Okay, this is lecture 32 of Basic Calculus 1. So, in the last lecture, we had discussed about computing volumes of certain kinds of solids by using the slice method. So, today we will be talking a particular case of that slice method, which is called disk method. This is applicable to again a subclass of those solids which we have discussed last time. So, specifically we will be using the solids which are generated by revolving certain area around a straight line. They are called solids of revolution. So, there the slice method is renamed as the disk method. We will see how do we go. So, first, what is a solid of revolution? So, solid of revolution is a solid which is generated by rotating a planar region about a line. So, that line is called the axis of revolution. For example, if you take a line and raise one rectangle around it on it. So, it is a rectangle. Suppose you take this as the axis of revolution and this rectangle side has say A and the other side is say B. So, now when you revolve it around this straight line, you would get one cylinder. Okay. That is how you will be having a cylinder of height B and the circular base, that circle is having radius as A. So, this is an example of a solid of revolution. So, similarly, it need not be this rectangle, it can be some type of say some planar region and the straight line may not be intersecting or even touching that planar region, it can be somewhere else, and we will see how if you revolve it the area around this line, you would get a solid of revolution, and then this is we want to compute the volume of such a solid. Okay. So, once you have a solid which is obtained by revolving a certain planar region around a certain line, then how do we go about computing its volume? Okay. So, that straight line is called the axis of revolution. Now, to make it convenient, let us take that axis of revolution, that straight line as our x axis in the plane. And suppose the plane region can be described now with this axis and have a perpendicular y axis also in the plane. Suppose this is a region bounded by a curve y equal to f x, the x axis, the lines x equal to a and x equal to b. So, we are taking a very particular case, we will come to a slightly general case later. So, it is something like the axis of revolution and you have a curve y equal to f of x, you have a line x equal to a, you have a line x equal to b, and now you are revolving it around this plane, around this line. So, you would get some solid of this kind. Okay. This is how the solid of revolution are formed, and we are taking a particular case where the line itself, the axis of revolution itself is one of the boundaries, right. There are the whole boundary consists of this line and something else, specifically x equal to a, x equal to b and another curve. Okay. For this kind of solids, what we do? First we take a cross section perpendicular to the x axis, we want to use the slice method. So, once you have some solid of revolution here, we take a slice here. So, that means you take any cross section perpendicular to the x axis, right. So, that is our x axis now. Now, at any point C, or you take the area of this cross section. So, since it is x, this one is equal to y or f of x, that height or the radius of that circle which is generated here, it will have radius as f of x. Therefore, its area will be pi times f of x square. So, the cross sectional area is a x, which is pi times f of x square. Therefore, the volume of the solid by using the slice method is equal to integral a to b pi times f of x square dx. This will be our generic formula in the disk method. So, we call it disk method because we are obtaining a disk which is the slice. Okay. So, under all these conditions only we write, and we have that condition that pi of f x square in the integrand, it is really integrable function. So, usually we will assume that it is continuous, f of x is continuous. So, now what kind of solid we are generating and for which it is the volume, we must remember that it is the region bounded by y equal to f of x axis, that is the axis of revolution, and the lines x equal to a and x equal to b. That is why you get the limits as a and b for x, and then it is the area of the cross section which is pi of f x square dx. So, that is how the volume will related to this kind of solids. Okay. So, that is why it is called disk method, because the slice now the cross sectional area becomes a circle or a disk. It is a disk because we are taking the solid. Okay. So, let us see an example before going further. So, the region between the x axis and the curve y equal to root x. So, we have a curve y equal to root x and the lines are x equal to 0 and x equal to 4, right. So, the region is defined by y equal to root x, the x axis, and x equal to 0, x equal to 4. So, such a curve, once you take the curve, this curve is revolved about the x axis, and along with this 0 less than or equal to x less than or equal to 4, you get a solid of revolution. We want to find the volume of that solid. So, this is how it looks. You have y equal to square root of x, which is the blue one here, and then any x lies between 0 and 4. So, you get some solid here. That solid is obtained by revolving this curve, in fact, this region about x axis. So, that is how it looks. This is the region. So, that region is revolved around x axis to get this particular solid. Okay. So, according to our formula, the volume should be equal to 0 to 4 and then pi f of x whole square, that will be the integrand. So, now f of x is root x, so its square is x, then you get 0 to 4 pi x dx, whose integral is x square by 2 multiplied by pi and evaluated at 0 and 4. So, that gives 8 times pi, right. So, volume of this solid is equal to 8 pi. Fine. We take one more example. Maybe the examples itself will through the examples will introduce other kinds of regions which when revolved give rise to different kinds of solids, but all of them are called solids of revolution. So, here we want to find the volume of the solid generated by revolving the region bounded by the curve y equal to root x like the earlier one, but now line is not starting at 0, it is at the lines y equal to 1, x equal to 4 about the line y equal to 1. So, that means we are not revolving it around x axis, we are revolving it around the line y equal to 1. Okay. And the region is bounded by this curve, the line y equal to 1 and x equal to 4. So, how the figure look like? We have y equal to root x, which is the blue one, is the curve here, and then y equal to 1 is the line here around which we have the region. What is the region? It is bounded by the curve y equal to root x, the lines y equal to 1 and x equal to 4. So, this is the line x equal to 4, this is the line y equal to 1 and this is the curve y equal to root x. So, the region is painted now blue. This region is revolved around the line y equal to 1. Okay. So, you would get some solid of this type, which is painted green here in the second picture. We want to find the volume of this solid so generated. Okay. So, first thing we have to find this disc, what is the area of this disc, and that should be just giving from our formula, it is pi times f of x square, but it is not just f of x, because the line is now y equal to 1. So, you have to get its radius really. So, what is the radius here? It is this line here, which is painted pink. So, since this is y equal to 1 and this point is y equal to root x. So, this one is the height is now 1 and this height is root x. So, it is root x minus 1, that is really the radius of that disc. Radius of this disc is root x minus 1. So, our a x will be pi times root x minus 1 whole square, and that is to be integrated from where? It is the line y equal to 1, and what is the other limit? You have, since y equal to 1, it says x equal to 4 is the other line. So, what are the limits of the integration? Once you revolve it around this, it is, this value is at 4. So, this is 2, this height is 2. Therefore, once it is y equal to 1 and it is revolved around. So, this is the other height, which is also 1, right. This height is really 1, this total height is 2. So, this is also 1. Then once it is revolved around, it will touch the x axis as shown in the green picture here, fine. So, since it is revolving around y equal to 1, we must find out what are the limits for this integration. So, integration is for x now, it is on the x axis, at this point it is x equal to 4 and on the left side you have x equal to 1, right, because this is the point where it crosses the y axis and that height is y equal to 1. So, x is also equal to 1 from this function y equal to root x. So, x limit is from 1 to 4. Therefore, volume equal to integral 1 to 4 pi times root x minus 1 square dx, and now it is a matter of integration. So, this we expand, it is pi goes out, root x minus whole square equal to x minus 2 times root x plus 1, and its integral is x gives x square by 2, root x gives 2 by 3 x to the power 3 by 2 and 1 gives x. So, this is the correct expression. It has to be evaluated at 1 and 4 and then subtracted. So, after simplification you would obtain the volume to be 7 pi by 6. So, here as you see, we have to really find the limits for integration, and the limits will come because of this point, which is obtained by the curve and the line y equal to 1, their intersection. In some of the problems that might be given from which line to which line, but here it is not given, it is just about the line. So, we have to find it out, and that turns out to be y equal to 1 crosses the curve y equal to root x at the point 1 comma 1, and we get the limit for x as 1, and the other side of course, it is x equal to 4, okay, as it is given in the problem. That is how we get the limits. So, we have to get the limits, we have to get the radius of that cross sectional area, which is a disc, and then plug it in the formula. Okay. So, let us consider another example. Here we want to find the volume of the sphere, which we know of course from other places, but we want to see how it is, how our method is applied to compute the volume of the sphere. So, the sphere is given as x square plus y square plus z square equal to a square for some positive number a. So, we want to find the volume of this. So, that means we have to think of the sphere as a solid of revolution. Okay. So, this sphere has radius a, and how do we take it as a solid of revolution. So, let us say we look at the semicircle x square plus y square equal to a square, say x square plus y square equal to a square, it has radius a, and we take only the semicircle which is say y greater than or equal to 0, which means we just consider this semicircle where this is 0 and this radius is a, this is x axis, and then we revolve this semicircle around x axis to obtain the sphere. Okay. If you take the whole circle and revolve, you also get this sphere, but you in fact get twice the sphere, fine, because they are repeated. Now, there is no repetition here in the obtaining the solid of revolution. So, we take the semicircle, and moreover, now once you take the semicircle, this really is a function. Okay. So, the function you can write y equal to square root of a square minus x square, that is the curve. Okay. So, now this is the curve y equal to square root of a square minus x square, and this is revolved around x axis with obvious limits minus a to a. Therefore, volume of the solid will be equal to minus a to a, and the cross sectional area with the disc. So, what is the disc now? The disc will be here, it is generated here. So, this is the disc. So, that disc again has the same radius as a, but it is at any point x, not in the middle. So, if it is at any point x, something like this, say this is x, then its radius will be this y component, which is square root of a square minus x square. So, the cross sectional area of the disc so generated is pi into square root of a square minus x square whole square. So, volume is equal to minus a to a pi times square root of a square minus x square whole square dx, and that simplifies to pi times, it is pi times a square minus x square, and that integral will be a square x, and for x square you get x cubed by 3. So, it is pi times a square x minus x cubed by 3 evaluated at minus a, and then subtracted. So, you simplify to get 4 by 3 pi a cubed, as you know the formula of the sphere of radius a is, right, volume of the sphere of the radius a. Okay. So, let us take another example. Here it is so complicated now, but let us read it slowly what happens here. In the figure is shown a solid with a circular base of radius 1. So, look at the first picture, which is in multicolored thing, brown, red and slight blue. So, that says it has a circular base of radius 1. So, here is the base, it is a circle of radius 1, this is 1. Okay. In such a way that parallel cross sections, so these are the cross sections here, these cross sections perpendicular to the base are equilateral triangles. Okay. So, that means if you take the cross section, it will not touch the circumference of the circle, it will go like this. So, that becomes an equilateral triangle. So, the triangle will be looking like this, where it is pink, it is an equilateral triangle. At every point you take the cross section parallel to that, then you get an equilateral triangle. So, what we do? We look at it in a different way, take the axis as x axis, which is the which goes through the its middle in the base. So, let us take that as the x axis. Then you look at this triangle which is formed, which is pink here, colored in the second picture. So, that triangle is an equilateral triangle, and everywhere it becomes an equilateral triangle. That is how it looks, and you have a circular base. Okay. So, I think the pictures depict it correctly. Then we have to find out the volume of this solid. First thing is we have to see it as a solid of revolution, and then of course, we can apply. So, now take the base of the solid as the disc, square root of x square plus y square less than or equal to 1. So, since this is the x axis we have chosen, now the solid of this is one circle, or a disk really. So, that disk is x square plus y square less than or equal to 1. Okay. The point B is the point here, which is the cross sectional area comes here. So, that is printed here B in the second picture, that lies on the circle, right, which is the boundary of this disk x square plus y square less than or equal to 1. Therefore, in the plane x y, that y is equal to square root of 1 minus x square. So, that is clear because this is B x y. So, that gives rise to y equal to square root of 1 minus x square. Okay. So, the length of AB, we want to find the length of that equilateral triangle. So, length of AB will be equal to twice of that because the axis x axis goes in the middle of it. So, that should be equal to twice of square root of 1 minus x square, that is AB. In fact, that is the side AB equal to BC equal to CA equal to 2 times square root of 1 minus x square. We need to find the area, right. This is the cross sectional area. So, we can use the slice method directly because disk method is anyway coming from the slice method. So, let us see that way how it goes. So, once the base is or the side of the triangle is 2 square root of 1 minus x square, we want to find its height. Okay. So, we come back to this pink picture here. What happens if this side is y, this is y, where y equal to square root of 1 minus x square, then its perpendicular length, because all the sides are same. So, it will be root 3 times y, right, because this side is 2y. So, it is 2y square minus y square square root, that is equal to root 3 times y. So, perpendicular is root 3 times y, hence the area of triangle ABC we can find out now, which is half root 3 y into 2 y, right. So, 2 gets cancelled, we get root 3 times y square, and what is y? Y equal to square root of 1 minus x square. So, it is root 3 times 1 minus x square, right. So, that will be the area is root 3 times 1 minus x square, fine. So, once we have got the area of that cross sectional area, this cross sectional area is really to be integrated over minus 1 to 1 to get the volume. So, volume is minus 1 to 1 Ax dx, which is minus 1 to 1 1 minus x square dx, root 3 comes out, which turns out to be 4 divided by root 3.